Hi everyone, we are back and we are going to wrap up with a discussion of fatigue. So fatigue is another kind of insidious mechanism similar to creep, where a material, whereas creep was a material will yield at stresses much less than our yield stress, fatigue will occur if we have some type of cyclical loading where the stress at failure is going to be much, much less than the actual predicted stress at failure. So it will fail at stresses much, much less than this value. So for fatigue, we're going to monitor effectively an initial crack length and see how it grows or what is the crack growth rate over a certain number of cycles. So this is effectively our crack growth rate here. So you can have static fatigue where you just have a static stress and you see how this grows over time or over a number of cycles. You could have cyclical or classic fatigue and lots of different types. And you characterize fatigue using these stress ratios and looking at the minimum or the maximum stresses. And there are three basically growth regimes. So slow growth, similar to kind of our initial creep rate. And we're basically given a relationship where we can use fracture toughness and the change in fracture toughness to basically examine how that will grow. The typical regime that we examine is the mid-growth rate regime or the Paris regime, where we have this kind of somewhat constant crack growth rate as a function of our change in our fracture toughness, and then finally in regime 3, that material is going to fracture almost instantaneously because you see that almost exponential growth in that crack length. So we can actually predict and characterize this relationship between crack growth rate versus our basically change in our fracture toughness, which is proportional to our basically this expression here, our change in stress for the cyclical fatigue. So again, this would be, if we're looking at, versus time and stress, this would be our sigma max, this would be our sigma min. So that's your basically change in growth is just sigma max minus sigma min. So we can integrate this function and you can actually predict as a function of these different variables. So this is our critical crack length. This is our initial crack length. M and C are basically constants. And as a function of the applied stress, you can predict the number of cycles to failure. Typically, you'll see this more often represented in SN curves. So this is looking at your delta sigma, and you're seeing if I apply this delta sigma, my stress amplitude, and I go here, I can survive this number of cycles until I fail. So you're basically drawing lines to see, okay, at different stress amplitudes, I have lower numbers of cycles until it fails. At smaller stresses, which makes sense, I can kind of hit forever. Or you can see, if I'm looking at the green curve, I'm never going to cross because it plateaus, so I never have to worry about fracture in this scenario. And again, you can calculate that critical crack length from our previous expression for fracture toughness. So that is it for our venture into mechanics. So next we're going to get into electrochemistry. So we'll see you all in the next video. Thanks. Bye.